So we're back in the IntelliJ project for my EX22 folder, which is in the RxJava directory in my live lessons GitHub repository. So it's the EX22 project that's in the Java 8 folder in that particular GitHub live lessons repository. And we're going to take a look at something called fork join tests. And these are all the methods we looked at before in the EX22 driver program that show off different ways of performing fork join operations. And we're going to start with the most basic one in some sense, which I call apply all iter. And apply all iter takes a list of elements of type T, which in our case are big integers, of course, and a function, which in our case is going to do reductions and multiplications on each of the elements in that list, which is generated randomly. And it also takes a nice, fresh, new fork join pool. So we've got ourselves a nice, fresh, new fork join pool. And what we're going to do then in apply all iter is we're going to use the fork join pool's invoke method. And invoke basically will block. So it'll start off a recursive task, as we're going to see in a second. And that will then go run in the context of the common fork join, or not the common fork join pool, the fork join pool that we give here, that we use to invoke the invoke method on. And it'll go ahead and run that task. And we're going to define what that task is, as we show here. It's basically sort of an anonymous inner class. And this is the task we're going to run. And this task, as you'll see in a moment, is going to fork off a bunch of other tasks. And all those tasks will initially start out in the calling thread, the initial thread that handles this, which is one of the worker threads in the fork join pool that we pass as a parameter. But very quickly, the other threads in that fork join pool will start stealing the elements from that deck in that one thread. So you remember each worker thread in the fork join pool has a deck, and that deck is used for stealing. And so that one thread, which will have initially all the elements in its deck, will have those elements stolen by other threads. And that's why its steal count is so high, because pretty much every single element is stolen by some other thread. So let's go ahead and take a look and see how this works. First thing we do is we make ourselves a list of fork join task objects. We're going to make it a linked list. We can make it an array list too if we wanted to. And then we're going to make ourselves a linked list to hold the results. Again, we could use an array list if we wanted to. And then for each element in the list that's passed as a parameter, which is that list of random numbers, we're going to go ahead and add the following anonymous inner class, or lambda expression, I guess is a better way to look at it. We're going to add this lambda expression to the forks list. So we're making ourselves a list of fork join tasks. And the fork join task list is going to basically say, take the op that's passed in as a parameter, apply whatever function it is to the element in the list, and add that to the forks list and fork it. So what we're doing here is we're actually forking something and adding what's forked to the list. So we're basically forking a task, which, as you may recall, enqueues it in the deck, the calling thread's deck, in the worker thread in the fork join pool, and we're arranging to have that run in some worker thread. It might be this one, it might be some other thread that steals it. So we end up with an array, or rather a list, a linked list of all these forked recursive tasks. And they're all going to basically then start the wheels in motion. And everybody's going to go off and steal, and do the processing. And then this main thread will then loop through all the elements in the forks list and join with each of them and add each of the results returned by join to the results list. And when we're all done, we return the results. So we end up basically with a list returned here at the very end. And the thing to remember about the way this works is when task join is called, it doesn't actually block the calling thread. It allows the calling thread to pitch in and do more processing until the task that it is joining on has completed, in which case it returns its result and adds it to the results list. So the way to think about this again is you've got a nice big full deck, playing with a full deck. We've got basically 100 elements that go onto that deck, and then all the other threads start stealing those elements and processing the results. And then the main thread, the calling thread, once it's finished, essentially forking everything, it then goes into a loop and joins. Each time it'll basically join about 100 times, gets all the results back, and then it returns the results. Now, as you might expect, that's fairly easy to program. It's fairly straightforward. You just loop through the tasks and fork them, and then you join them all. But a lot of steals are involved, and that made the overhead a little bit higher. Let's take a look at a different way of doing things. This is called all split index, and there's a couple of different ways we can do this. Let's see if we can look at the one all split first. So this approach is going to avoid using that single deck with all the elements, all the subtasks thrown into it. Instead, it's going to basically recursively split the calls. And so by recursively splitting things, that's going to allow the distribution of tasks to be more evenly balanced, and so we'll have fewer steals. So let's take a look and see how that works. We're going to define a nested class called splitter task, which extends recursive task parameterized by a list. So basically, we're going to take the overall list and split it into sublists, and that's what splitter task does. And it does this with its compute method. Well, first, its constructor just takes whatever list it's passed and stores that here in this original list. And then what we're going to do is we're going to define the compute method. Compute is what we get when we extend recursive task. It's a method that needs to be overridden, and I probably should be override, because we're overriding a method that was defined to be abstract. And we check to see if the list has got only one element in it. We're going to make a new result list, and we're going to add the elements to it, the one and only element, after we apply the operation, and we return that result list with one element in it. Otherwise, the list has more than one element, and we're going to do good old divide and conquer. So with divide and conquer, we figure out the size of the list, we figure out where to split it, and we make a new splitter task that will essentially take the left-hand side of the list, and that's what this thing is. It's from the beginning of the list to the midpoint, which we computed here, and we go ahead and make a task that will handle the left-hand side of the list, and then we go ahead and we update the list to now only include elements from the midpoint to the end. So sublist basically is going to take a sublist of the original list and update the original list. So now the right-hand part is handled by this object. The left-hand part is going to be handled by a new task. And then we call compute to compute recursively the right-hand side, which is now sliced in half. And then we join the left-hand side after compute finishes. So when compute returns, we then go join with the left-hand side. We need to do it in that order because we want to have this fork get a chance to run in the background, and we don't want to be calling compute until we fork it. And then we go ahead and join. And then when we're all done, we take this left-hand side and we add it to the right-hand side, and we return the results. So what we're basically doing is we're splitting up the original list until each element has only one item in it. Once each sublist has only one item, and then we apply the operation at that point. And when we're all done, you can see that not when we're all done, when we start things off, you can see that the last line in this class, apply all split, calls fork join pool invoke, calling splitter task on the entire list. So we start out by giving it the entire list, and then this code recursively breaks it up into sublists and then joins them together after they've been split and forked. You'll notice that this particular implementation returns sublists. So it extends recursive task because it has a type that's coming back from compute. The downside with that approach, even though the number of steals is nicely low because we do recursive decomposition. The downside is we have to do all this list operations. There's lots of copying of lists, and there's also a fair number of recursive calls, whereas the original code we saw earlier up here in apply all iter, this one, that didn't have a lot of extra function calls because it wasn't doing recursion. So we're going to come up with another approach here called apply all split index. And this is a very clever approach that doesn't use recursive task for splitting, but instead it uses something that's called recursive action. And a recursive action does not have a return type, whereas recursive task does. And what we're going to do in this particular case is we're going to use indices to keep track of where we are in this overall list and not have to do as many copies. So as you might expect, this approach is slightly faster typically because it's not having to do copies. Now, the one thing it does have to do, which is a little bit wacky, and this is just a virtue in quotes of Java's half-hearted support for generics, we have to use Java reflection to make a new local variable called results that will hold the results that we want to pass back to the caller. So we're going to make ourselves this results array, and we do it by using array.newInstance and some other gobbledygook. You can find how to do this stuff on the website. If you watch the videos, it'll give you the link to where to look for this. So we make ourselves a local generic array. And I wish there was a cleaner way to do it, but that's the cleanest way to do it that I've found. This code is more or less the same as the code we saw before, but the big difference now is that we're splitting things using indices, not sublists. So as a consequence, we find the midpoint by taking the low and the high and basically dividing by 2 or right shifting by 1. Probably overkill to do it that way. You could do divide by 2 and it would turn into the same code with the optimizer. And then if we have only one element, we call apply. And if we have more than one element, we call splitter task, splitting things from low to the midpoint. And we fork that. We then compute ourselves. And then we go ahead and join with the left subtask after it's finished being processed concurrently. And the way that this thing works, you can see the invoke method creates a splitter task that starts out initially from 0 to the end of the list. And when we're all done, we will have a results array that contains the results of adding those elements to them by applying the operation to do the reduction and the multiplication. And then we convert that back to a list by using the list of factory method. So that's the apply all split index method. Now there's also another mechanism here, which is a little bit more clever, but it changes the signature ever so slightly. Rather than have to do this wacky reflective approach to get ourselves a local array of type T, another approach, which is way cleaner and probably faster too, is just to pass an array of type T as the fourth parameter to the apply all split index EX method. And so this has a slightly different signature. However, it's a lot cleaner, and you don't have to do all the craziness by converting things back and forth between lists and arrays. So it basically just goes ahead and updates that array in place. And then when we're all done, it just has the results ready for the receiver when it gets back from the call. The other methods here are variations on other themes that are worth talking about briefly. It turns out that there's a method that's part of the fork join pool called invoke all. And if you give it a collection, it will go ahead and run all the computations at the same time. If you give it a collection of callables, it'll go ahead and call them all in parallel using the fork join pool to do so. So to do that, we make ourselves a new list of callables. We use an array list here. And then we go ahead and we add a bunch of callable lambdas that will apply all the operations to all the elements in the list. So we have little lambda expressions that will apply them, and we add all those lambda expression callable lambdas, as I like to call them, into this tasks list. And then we say, hey, fork join pool, please go ahead and invoke all the tasks. Thank you very much. And we get back from that a list of futures. We turn that into a stream of futures. We use the map method from Java Streams to convert those into a stream of elements of type T by using future get in conjunction with the rethrow function, exception laundering method. And then the results are returned as a list of elements of type T. So just kind of demonstrating how you can use invoke all instead of having to write all this extra code for splitting and so on in order to get the job done. And then the final method, which is arguably the simplest of all, is to use the parallel stream method. And you can see that in this case, we take a list and a function. There is no fork join pool because it's going to use the common fork join pool. That's what parallel streams do. We say, hey, list, turn yourself into a parallel stream, apply the mapper function to each element in the stream, and convert the results that you get when you're done back into a list. So that approach is clearly the simplest of all the approaches that we looked at. And when you look at the results, you can see that it doesn't execute horribly. It's maybe about half a second slower than the other ones. And that's most likely just because Streams is doing more stuff for you under the hood. And these other approaches like test apply all split index EX, that's the one that has you pass the array in, and it's pretty nicely optimized and it splits things nicely. You can see that the steal count is super low. It does have some recursive calls, but not that many. And because it's splitting it, so it's basically log base 2 of 100, which isn't very much for recursion. And there's really no data copying. There's no extra data copying and things like that. So these examples, this example, the EX22 example, shows off a whole slew of different ways of programming the fork join framework in modern Java. And because it's kind of taking the fork join framework, which was actually not strictly part of modern Java, that was in Java 7. We don't consider modern Java until Java 8 comes along. But it's kind of combining the fork join framework mechanisms with some of the other modern Java stuff like sequential streams and other things to give you some more flavor to what's going on here. So that's the end of that example.